There we are. Thank you. Hi, everyone. Yes, technology case study was the only title, and thank you very much for being curious enough to see what it's about. This is about a technology developed by Seagate. It took them about 20 years to develop, called heat-assisted magnetic recording, HAMR. You'll have heard about HAMR drives. And I'm going to go into a deep dive over the next 20 minutes into this technology, and I hope you'll agree with me. It is truly one of the most exquisite technologies. Coming from myself, coming from a photonic interconnect background, looking at HAMR which was new to me a few years ago, it is exquisite, incredible, precise engineering, which solves many of the problems that we have in photonic interconnect, and the Seagate don't seem to realize it. So that's good. So I will talk briefly about optical interconnect in hyperscale data centers, because we started out developing a lot of the precursor technologies to co-packaged optics in the UK, in my team. And then I will move on to talk about photonic integrated circuits and the deep HAMR technologies. So optical interconnect hyperscale data centers, no surprise here. Hyperscale is a term we give to very large data centers, maybe at least 100,000 servers. And since about 2021, it is the dominant form of data center in the world in all metrics, in terms of traffic, volume, data storage, and it's the type of data center used to administer cloud services. So Amazon, Microsoft, Google, these are all hyperscale data centers. And optical interconnect is intrinsic to them. So here, for example, in this image, you see these yellow gantries. They're all carrying optical fibers. This is not a surprise. But in the last decade, say starting from 2012, Seagate Systems in the UK were looking very carefully at the limits incurred by very high-speed electronic interconnect, and how do we incorporate optics, spring optics into the box. So the precursor to co-packaged optics leading up to co-packaged optics. So we involved in a number of European projects. These are the projects here, Cosmic, Neptune, Foxtrot. There are other national projects as well. But this is all looking at how we could take data center systems, the systems we were developing, and bring optics into it. So some of the key technologies I'll be showing here. This was a data storage array called Pegasus, and it had an Ethernet switch in it. So this is an Ethernet switch controller. And we developed mid-board pluggable. So we developed mezzanine cards, which allowed us to put in different types of mid-board pluggable optics, including PICs and other technologies. And so very, very basic demo. But this is the start. Then we developed the entire ecosystem for bringing optical interconnect in, including this kind of thing here. This is a 192 fiber flex plane, just in the brown sections here. And we were looking at polymer waveguide boards. This board shows a cross-section with two cross-sectional polymer waveguide boards developed by TTM Technologies. And we developed a disk drive which had an optical interface. So this mezzanine card, it's an interface which allows us to take a standard disk drive and convert it into an optical interface. And for this we used it doesn't exist anymore, but this is a transceiver developed by Murata at the time, a 2+2. And we developed a special optical connector for that. And so this is a disk drive with a modified electro-optical interface. You have electronic interconnects, high-speed electronic interconnects, and you have, in this case, this was a Prism MT by US Connect, which had 64 microlens channels. We only needed one of them. But we were just demonstrating that you could incorporate this onto a drive. And so we developed microservers and disk drives which could be put into the same drive carrier, and that means you could interchange drives and microservers in different ratios. And then taking this forward, we were working with our various European partners to incorporate photonic integrated circuits. This is from CA Leti. In France on a project we ran. This is a few generations of WDM silicon photonic transceiver. This first generation had a vertical grading coupler. The second generation had an adiabatic coupler. More or less obsolete now, the adiabatic coupler. Vertical coupler is dominant. But we developed the abilities to put this into systems, and we developed international standards to accommodate this. And here are some close-up images of the silicon photonic transceivers in question. It was heterogeneous. The larger shiny bit is the PIC, the photonic integrated circuit, And this part is the electronic integrated circuit, which was on top of it, which was driving the phase shifters on the photonic integrated circuit. And here is the second version, which had this black area here is the adiabatic coupling region. So you etch back, and you take silicon single-mode polymer waveguides and press them down. But that was just an amuse-bouche. I'm going to be talking about the HAMR technologies now. So photonic integrated circuit technology, it is, in essence, it is an integrated circuit technology in which you're able to guide light and in which you're able to manipulate the speed of light. And if you combine these two very simple abilities, you can do anything. You can modulate light using interference effects. You can split light by wavelength, by power ratio. You can mux, demux light. You can develop neuromorphic computers. You can develop all sorts of things. The most common material platform for this is silicon, because we have CMOS architecture in place now. The indium phosphide is still very small, by which I mean not the lasers, I mean the indium phosphide PICs, sophisticated photonic integrated circuits where you include lasers, detectors, and waveguides and light manipulators all on the same chip. Silicon nitride, in Europe we have Ligentech and Lionix, and I think there are some in the US which are great foundries for this. Silica glass, Team Photonics in France, for example. Polymer, by which I mean electro-optic polymer, you have Lightwave Logic in the US, you have NLM Photonics, Brad Booth just became CEO of NLM, by the way. And this is interesting because this is a key for low-power optical modulation. So low-power transceivers, you need to start looking at these kind of low-power phase-shifting materials. So polymer, lithium niobate was mentioned, thin-film lithium niobate. Barium titanate is a relatively new material. There's only one company in Europe, which is Lumiphase, a spin-off from IBM Zurich. And they developed barium titanate, which in principle has a higher electro-optic coefficient than lithium niobate, but it has many challenges when it comes to patterning. Anyway, many applications for photonic integrated circuits, optical transceivers being the most common one, but also WDM switching as part of optical networks, neuromorphic computing. We heard from Lightelligence, and there's other companies like Matter, which look at this. Wearable diagnostics, Rockley Photonics, and other companies. The ability to non-invasively monitor your blood and read glucose and other diseases is the holy grail if it can be gotten to work. And combining that with AI data sets. Sensors for gas, LiDAR, and quantum technology. In fact, I'm going to be giving a talk this afternoon on quantum standards, and I'll also be talking about quantum PICs. And HAMR. So that's my segue into HAMR, into heat-assisted magnetic recording. First of all, high-capacity digital storage. The need for I'm sorry, this is quite an old market report that they give me here from 2018. Maybe you can give me a better one, Vlad, later. But anyway, exponential increase in data storage demand is not a surprise. The question I get asked a lot is, we have solid-state drives and hard disk drives. Why do hard disk drives even exist? Are they not obsolete by now? And it's true, there are many advantages of solid-state drives. They're better for performance sensitive, for fast transactions, so-called hot storage, where you need rapid change of data storage. But overall, hard disk drives still provide the best total cost of ownership for the majority of cloud workloads. That's simply a fact. And it is, many people say it's very simplistic, it's a glorified record player, but that's absolutely far from the truth. It's an unbelievably amazing technology. Now, I'm going to give you a quick introduction to how hard drives work. You have a magnetic platter. Your data is much like a CD. Your data is stored on a disk in little domains, but in this case, it's stored in magnetic domains, and it's read and written by an electromagnet, which sits on a kind of gimbal, an arm. HGA stands for head gimbal assembly. And it reads it just like a record player would read it. So in principle, that's the principle. But the truth of the precision involved and the dimensions involved are absolutely staggering. First of all, magnetic regions. If you take a magnetic material, an alloy, usually a cobalt-based alloy, you have a magnetic surface, and it's divided into grains, and each grain has magnetic domains. What happens with these alloys is if you cool it below a temperature called the Curie temperature, spontaneously you get the magnetic modes divided in what are called magnetic domains. They're very, very small. You have magnetic grains, which are larger than that. So you've got a picture of that. magnetic grains, polycrystal grains, and contain many of these magnetic domains. And in order to capture a bit, we have many, many grains. So many of these here are actually grains. This is domains, but I think they meant grains. So a magnetic bit is the magnetic region we use to capture one bit of information, and that contains many grains. And this density over the last many years has been increasing. So that means that the magnetic region has to get smaller and smaller and smaller. The region representing a bit has to get smaller and smaller, and that's a big challenge. So reading and writing on a magnetic platter, the principle is simple. You have an iron core, you have an electromagnetic coil of copper wire, and by depending on the direction of the current that you pass through it, you can either create a magnetic field in one direction or the other. This is the oldest method called longitudinal magnetic recording, and here you have the magnetic platters. You also have a very sensitive read element, a GMR, giant magneto resistance sensor, which uses a quantum effect to read changes in magnetic domain. So as it passes along, it reads a change in magnetic domain and captures this. So what happens is you pass this along here and you write by choosing the card each time to set your bit direction, and you read at the same time. The read head is on the same head. But in order to increase the areal density, they developed a technology called perpendicular magnetic recording. So essentially, they took the domain and they made it long and thin rather than spread along the area. And for this, they needed a soft material underneath the magnetic alloy. What happened here is that you change the shape of the right pole. So this one's very tapered, so the magnetic flux density is very, very, very high here, but on the return pole, it's spread out. So that means only where the density is highest is that sufficient to flip the magnetic bit, but here, when it's all spread out, it's not sufficient. So only here would you be able to write these much smaller bits. So that's how they achieve much smaller writing. And we have the same read element, and there you have the same principle again, except much smaller magnetic domain. So higher areal density was achieved with this perpendicular magnetic recording. One incredible feat of engineering here is when they're developing these head gimbal assemblies, they're essentially using aerodynamic engineering. It's like they're developing a plane wing. This gap, or what they call the flying height, the gap between the magnetic platter and the read pole, is about 5 nanometers. If you can believe it. Unbelievable. This is the kind of precision that in PIC circles, photonic integrated circuit circles, is almost unachievable from an alignment perspective. But this is what you find in every disk drive today. So they put an incredible advanced engineering, many years of advanced engineering to create this air-bearing surface, to create this wing. So that's amazing engineering. So if we take a closer look at the head gimbal assembly, you have a huge number of devices packed into very, very small areas. So if you look here, so within an area of 0.3 square millimeters, you have about 300 devices. That includes the read sensor, the write pole tip, and many other sensors and heaters and so on. Incredible density achieved there. I mean, can you imagine that type of technology deployed in photonic integrated circuit circles? The potential. I straddle both worlds, so I'm coming from the PIC world. So this is always really interesting to me. So areal density trilemma. So there's a need to increase the areal density on disk drives because you want to increase the amount of data that you can store on a magnetic platter. So you have this relationship. You have n, which is the number of grains in the magnetic bit, the region associated with a bit. But if you reduce the number of grains, you reduce the signal-to-noise ratio of the read-write capability. So in order to accommodate this, you must reduce the grain volume, the volume of the grain V. But if you reduce the grain volume, you also make it more unstable. So the magnetic domain is more liable to flip spontaneously. So you also need to. So then you need to increase a property called the magnetic anisotropy, which is the stability, of the magnetic domain. Its resistance to flipping spontaneously. But if you increase the magnetic anisotropy, you need a stronger magnetic field, right field, to flip the domain. So this is the trilemma. This is what you have to satisfy to increase areal density. And here we see a graph with some different alloys. Anisotropy goes up, and the ability to make denser, smaller grains also grows up. So these are the kind of technologies that will be the alloys that are being used now in disk drives. Areal density, look at areal density, over the last few decades. 1997, magnetic bit size was 103 nanometers by 80 nanometers. A few years ago, 21 nanometers by 10 nanometers. Unbelievable. That's the bit size. That's the amount. That's the area on the magnetic platter capturing a bit. And this is the associated reader size. And the writer size has to be, of course, of a similar order of dimension. So why do we need HAMR recording? Well, you have this shows the areal density profile over the years. First of all, longitudinal recording, which I described, and it plateaus. Then perpendicular recording, and then it plateaus. So we need a new type of way of creating smaller magnetic domains, smaller magnetic regions. So for this, we use the concept of heat-assisted magnetic recording, and this concept is as follows. You take a magnetic domain, and if you heat it up, first of all, your flux density here, your magnetic right flux density is too low to flip these domains, these bits. But if you heat up one of them, what happens is the area that you heat, the coercivity goes down, the ability to flip a domain essentially goes up, and only when it's heated past this temperature can it then flip under the magnetic field right strength. So even though the magnetic right field is much larger, covers many of these smaller magnetic bit areas, only the area that can be heated up will flip. And then immediately cools down very rapidly. It's very small, so it cools down extremely rapidly when you switch off the laser. So when it cools down, it's fixed in place. So you essentially melt it, you flip it, and then cool it. So this is done by, in simple terms, integrating a laser, an 830 nanometer laser, and a near-field transducer, which I'll explain in a moment. But essentially, you are using a laser, and it's attached to the same head, the right head and the sensor head, and you're flipping and melting and cooling all very quickly. And this allows you to create a much smaller magnetic region for writing and reading. Now, this is not a new concept. In the olden days, they looked at how do you heat up this area? Well, can we take a laser and just focus it onto a spot? Yes, but that's not possible now because, consider Blu-rays as an example. That's what they did. Blu-rays had a wavelength, lasers had a wavelength of 402 nanometers, but you have the diffraction limit. There is a fundamental limit as to how small the spot can be if you focus a light beam. So it's roughly about half the wavelength. So in case of Blu-ray, which is 402 nanometers, the spot size was about 238 nanometers. And this covers, tens of magnetic regions today. So this is way too large. The diffraction limit of light makes it way too large. So we have to find a way of just heating up a much smaller area or shining light on a much smaller area than the diffraction limit. You can block it. You can pass it through a kind of mask. But this, if you do this, you have this problem where as the radius goes down, the whole diameter goes down. It scales to the wavelength to the fourth power. That means you make the whole smaller by a factor of 2. You need 16 times more power to get light through it. So that's a non-starter because you need huge amounts of light to get through it in order to heat up one magnetic region. So what they use is an effect called plasmonics. And plasmonics is where you shine light on a metal surface. And this light is an EM wave. It stimulates oscillations in surface electrons. And these oscillations, these oscillating groups of surface electrons are called plasmons. And they propagate like light, but they have a much more compressed wavelength. And they propagate like light, so these electron oscillations propagate along the surface. This near-field transducer is essentially a resonance cavity for plasmons. Its shape is chosen in relation to the wavelength of light, such that when you shine light on it, you get this area here, this peg, in which all the plasmons coalesce, and you get the strongest EM field. And it is this peg which sits very, very close to the magnetic field plateau. When it's near the magnetic domain, it heats up a very, very small area, much, much smaller than the diffraction limit of light. So it uses plasmonics to heat up a much smaller spot than diffraction limit of light, so 20 to 80 nanometers, even though the wavelength of light impinging on it is 830 nanometers. So here's a nice another graphic essentially showing the same thing. This is the plasmonic effect. Shine light here, and you can find, and this shows you this thermograph shows you the area which is heated up. And this area here is called a peg. So this is called the near field transducer, this lollipop-shaped thing. Now, in order to to couple light to the magnetic reader, we use a waveguide technology. And you can see here from if I show you here, the waveguide here carries the light from the laser. It couples it, it's concentrated here, and it couples it to this near-field transducer, which is shown here. This lollipop design is shown here, and that's attached to the right pole and the return pole. So the heating element is right here, and you need this waveguide material to couple the light into this near-field transducer and confine it. This is another view of it, but this is your right and this is your right pole. These are your copper coils which you need to drive the electromagnet, and this blue section here is the waveguide material. The light or the laser is integrated further up, and it sends light here and then couples it into this plasmonic resonance. Here's some images just showing how very fine this is. You do need an integrated laser. And in case you haven't noticed, well, Seagate is the largest, I think the largest data storage. I think it has the largest market share of disk drives in the world. And huge volumes of disk drives are sent out. Imagine if this is sent out with lasers, you would have the largest photonic device in the world, the highest volume photonic device in the world, which no one knows about because no one knows there's a laser inside it. But you need a laser to make this work and to create the densities involved. And that is great. So if you want to look at high volume photonic packaging, this is a lot of these problems have been solved here. So areal density progress. So this is the areal density progression. So HAMR brings this up now. Further, it took 15 to 20 years for Seagate to refine and develop this technology and make it into, because they started selling it last year, it has to be as reliable as other ones. It took a long time, a lot of incredible engineering to bring this up. But this is an amazing technology now, and they've achieved areal densities which are mind-boggling. 50 terabytes per the target is we're very close to a 50 terabyte per disk drive target, for a hard disk drive target. So they started a year ago. They started shipping this for the first time after developing this for a long time. And it started from a patent in 1954, which was taking a lens and focusing it, and it's moved on to this. This shows an actual movie of sort of a HAMR gimbal assembly, obviously moving very, very fast. Just want to say we're in Europe, so not many people know this, but Seagate have a huge facility in Northern Ireland. I think it's the largest, probably the largest employer in Northern Ireland, and it's in Derry. Where they develop a lot of this HAMR technology, at least the recording head technology. They are, Seagate in the UK, they're involved in many European projects, many different consortia. One project in question is called Smart Nano NI, which is Strength in Places. This is an Innovate UK project where they are bringing together many Northern Irish companies to develop this photonics ecosystem. So that concludes. I've skipped the conclusion since I'm out of time. Thank you very much.
All right, thank you.